Thanks, Jared. Forgot. So, okay, good. Hopefully you can all hear me. Okay, good. I guess let's get started. I don't know how to fix that, but maybe I can just turn it off. Display to off. Let's leave it off. It's fine. So today I want to talk about statistical ray optics. It's interesting. There's only two of you today. That's okay. We have to go through some abstract things today, so it's going to be a little bit little harder class, I would say, but it's hopefully we'll tie it into some intuition. So anyway, that's my hope here. And I also want to, since you're here, in any case, I also want to talk about the last presentation, which is on the commercialization plan. So we'll go over that as the second part of this class as well. So this is where we are. So again, let me just remind you all also who are on Zoom and watching it later that those of you who are in the in-person class next week, they have a guest lecture by James. So make sure you actually are in the class. That's important because we have a guest lecture. Okay, so the statistical ray optics is a way or an approach to do analysis of very complex geometrical optics. So applying geometrical optics to very complex geometries like light trapping. And this is very important for solar cells. So I'll kind of go over what that means shortly. But before I do that, I just want to point out there's this whole approach is based on this paper by Eli Jablonowicz. It's an old paper from the 80s, and it's called statistical ray optics. So the basic idea is quite simple. So far, we've been talking about geometrical optics, right? And simple shapes like spheres, plane surfaces, parabola, and so on. Here, the idea is could we think about much more complicated shapes like random textures or hexagons or whatever? And of course, we know these random shapes are very important for solar panels, as we talked about anti-reflection coatings and things like that. So this is the basic concept. That is that can you use a statistical approach to understand ray optics or optical media with complicated non-spherical and non-planar surface shapes. Anyway, so if you want to learn in greater detail, I would strongly recommend reading the paper. It's a very important paper, in my opinion. And Eli is an interesting person. He's been nominated for the Nobel Prize a couple of times, actually once for the invention of the photonic crystal. Anyway, so that's what we'll focus on. So let me minimize that. And hide this. Right. Okay. So it is essentially geometrical optics for complex and random surface shapes. Now, why is random important? As we all know, random is important for light trapping, which you will learn about next week in a little more detail. But for today, now let's think about the basics. Now, basics will start from what we are familiar with in geometrical optics and in thermodynamics. So the basic concept, let's look at an example. So we're going to look at an example of a textured optical sheet. Oops. Look at it this way. So this is some optical material, okay, with some refractive index n, and that can change with position x and of x. And it's textured, as you can see, the surfaces are textured. And it is sitting in vacuum. And it is bathed by electromagnetic radiation, okay? We're thinking about this as black body radiation, but later on we'll remove that assumption. Now, when we have thermal equilibrium, what does that mean? That means this material here will be at the same temperature as its surroundings. So it's not going to lose or gain energy. That's the idea. Under those conditions, you have energy density inside this material given by an equation called the Planck's formula. Now, we don't need to memorize any of this, but the key thing to keep in mind is that this is the amount of energy. Oops. Someone trying to get in? No, okay. Amount of energy per unit volume that can be stored inside this material. That's essentially what it means. And of course, it depends on frequency. And it depends, most importantly, on this factor K here. Okay, and that K is what's called the wave vector. It's 2 pi over lambda, or in frequencies, is n omega over c. Now, the thing that's most important is this n here. In other words, this is it is directly proportional to the refractive index of the material. Now, what does that mean? Now, what we are interested in is intensity. So if you think about what is intensity inside that material, so you're shining light, you want to increase the intensity inside the material. Think about that material as a solar cell. So you want to make it much more intense in there. And intensity is given by something called the energy density. Okay, this is the energy density multiplied by the group velocity. Okay, and you can work out the units. Energy density is joules per meter cubed. Group velocity is essentially meters per second. This, the radians and so on, we can ignore it. If you multiply it, you'll get watts per second. Oh, sorry, watts per meter squared, right? We can do it. Joules per meter cubed multiplied by meters per second is joules per second meter squared, which is watts per meter squared, which is nothing other than intensity. Okay, so we know how to do this analysis from before. Now, the important thing is that when you do this multiplication, you end up with a term n squared here. All the other stuff are just constants and the dependence on frequency, which we're going to ignore for the time being. This means that the intensity inside the material is the intensity in the vacuum multiplied by n squared. This is the theoretically upper bound on the intensity that can be achieved inside this material. So let's see what that means. And why is that important? That n squared means that now you can increase the brightness of light inside a material compared to the outside by the refractive index. And that's a big term here. Now, so again, let me just make sure we all appreciate what is going on here. So what it means is that if I take a material, so some refractive index 3, that is silicon, and put it out in some region that has light, and if everything is completely thermally in thermal equilibrium, and there is the ergodic assumption, which we'll come to shortly, it means that inside the silicon, I can have n squared times the intensity of what's outside the silicon. And that n for silicon is about 3, so n squared is 9, so that's a big factor. That means I can increase the intensity in a material by simply choosing a material with a higher refractive index. So that's a very interesting and important point. By the way, it is also related to the concentration of light in the CPC case we talked about before. Now, there's a very important assumption in what we just said, which we didn't cover easily, in any detail, is that we are going to assume that the behavior of light is ergodic. And what does ergodic mean? Ergodic means it's essentially random. And random in the sense of the direction of light. So in other words, once the ray of light enters the medium, so I have this textured medium, and I have a ray of light, which is entering the medium. Of course, some of it's going to get reflected, some of it will get refracted. After a few different bounces, it is going to forget the direction in which it came from. That's the idea. So in other words, once it enters from the outside to the inside, it becomes completely randomized. This is what's called the ergodic assumption. And of course, this is a statistical point. In other words, you don't look at a single ray. Everything is deterministic. There's nothing completely random here. But if you average over a certain area, all the rays will get completely randomized. That's the basic concept. And it's easy to understand from the concept of removing memory of the direction. So again, as I said before, the intensity within a medium in thermal equilibrium with the black body radiation is 10 square times higher than its environment. We covered that, so let's keep going. Now, of course, in the case, we talked previously about black body radiation, which is uniformly distributed in the environment. Now, this is not always the case because you look at the sun, it's a direct radiation, so light is coming in completely collimated. So that's the situation shown here. So this does not have to be black body radiation. Now, what happens when the light comes in? After a couple of bounces, so there's one here, there's one reflection here, another reflection here, even with a few passage of interfaces, which can be refraction and reflection and transmission, you end up with completely randomized light inside. So you can actually show this mathematically, that as long as the rays are ergodic, that is, they forget their initial direction that they came after one or two reflections, which is statistically average. Over the area of interest. What does that mean? That means, of course, you start a single ray, you're looking at a beam of light, right? So you're looking at some area here. So if you average, and of course, in a volume associated with that area, if you look in that region, the ray, even though you came in with a single direction of rays like that, once you look inside here, it will be in all kinds of directions. That's what that means, statistically. Okay, so now let's look at a few examples of what that actually refers to. Okay, so here, whoops. Again, light's coming in from the top. We have a textured surface here, right? So light will undergo reflection and refraction. And then there's a reflective surface here. So what will happen to the light? Of course, we know some of this will bounce off. Some of this will refract in. And then here, because of the angle of this normal here, is going to bounce in some direction. And of course, some of it will transmit out, right? So let's draw that. We're going to transmit out. Now, what happens here? There's a mirror at the bottom, which is what's called the white surface. So it will reflect back. And here, some of it will, of course, transmit in. Some of it will reflect out, and so on and so forth. So you can see I have come in with one ray here. I've ended it with many different directions, right? I have a ray going this way. I have another ray going that way. And this is, of course, going to bounce around again. And then a ray going that way, and so on and so forth. So essentially, this one ray gave me 1, 2, 3, and so on, many, many rays. That's what went by the randomization. And of course, in this case, we are using this white surface here simply to make sure the light is reflected back into the medium. Now, because of that additional pass this reflector allows you to do, then you get an extra term of 2 there. So it becomes 2n squared. So I think those are relatively simple to understand. Now, one thing we didn't talk about is that this concept is only valid for very thin films, thick films. If they are too thin, you get interference, which we talked about in about 2 weeks ago. So one is that it has to be optically thick film, which means that the total thickness of that textured film must be greater than lambda divided by 2 times the refractive index of the material. And we have to ignore the absorption. There is no absorption in this material, which, by the way, is a problem, right? Because if this is a solar cell, you want the light to be absorbed. So if we're going to ignore absorption, that's already a bad thing. So we'll introduce absorption later on. So, but what does this actually mean? If you assume a wavelength of 1 micron, which is close to the band gap of silicon, and a refractive index of 3.5, which is silicon, what is the smallest thickness? This theory might be valid. You can calculate it easily. So 1 micron divided by 2 times 3.5. So 1000 nanometers divided by 7. So what's that? A few hundred nanometers. That's something like that. Okay. I don't know, 300 nanometers. And you can also ask, okay, well, how much enhancement intensity is possible? It's 2n squared. So it's 2 times 9, it's about 18. That's a pretty significant number, right? So if I can increase the intensity of the light inside the silicon by a factor of 18, that's a huge thing. Okay? So that's why this is important to kind of understand and see if we can take advantage of it. Now let's try to understand again what this whole ergodic thing means. And I gave you a visual picture. But if you think about a very, very symmetric situation like a billiard table, I can show, because there are only 90 right angles here, there are 2 lines, any billiard ball that is incident at any angle can only access 2 angles. The incident angle it came from and 90 degrees minus the other angle. Why? Because that's my incident angle. And I'm going to assume that there's no hole there. This will be also the same angle, actually. Now, this is a more interesting situation. This is 90 minus that. So you can only access 2 angles, the incident angle and 90 minus that. So it can never be ergodic. So in other words, it will never forget the angle it came from. So it's a highly symmetric structure. It is not ergodic. So whatever we talked about is not applicable anymore. So the number of angles accessible in a rectangular table with high symmetry is limited to 2. Now, what is the case if it was a circle? Anyone tell me? Guess I'll let you all think about this. Let me draw this better. Say that again, Chauncey. No, we are coming from the outside. So think about light coming in from the outside. So what will happen? So I'm going to draw first through the center. So what happens at this interface? What is the angle of incidence? If it's a radius, it's 0 degrees. So exactly. So it's angle of incidence is 0. Angle of refraction is also 0. So it'll go straight through. It'll do the same. Whoops, I drew this so bad. Hey, there's something wrong with my it is forming it's forming 2 pictures on my iPad here. So it'll go straight through. So there's no ergodicity. Nothing changes, right? It's exactly the same. Now, of course, I can change things if I come off axis. And then I have to draw, right? What happens? Let's say this refractive index is greater than 1. So it'll bend towards the normal. And then I have another thing here. It'll go up. Or it can be trapped if it's total internal reflection. But in any case, I can only access a few angles. It's not randomized. It's either escaping, but if it's trapped, it's total internal reflection, which just bounce around. All I can show is that it's no longer random. So it's high symmetry situation. But what's interesting is that this only happens in some special cases. In the vast majority of cases, when you have roughness, this will never happen. So that's the interesting observation here. So compared to the rectangular table, if you had a polygonal table, ergodic behavior very quickly appears. In other words, light bounces around a couple of times already, it's all more or less random. That's the idea. Of course, there's a big difference between what we've been talking about here and the case of the solar cell, because light is not like billiard balls, because it can, of course, have total interreflection, refraction. The billiard balls don't refract, right, obviously. And the systems are not closed. Here, the balls are essentially enclosed within that in the table, but light can escape by refraction if its angle is smaller than the critical angle, as we all know. Now, let's also think about the escape cone. So this is, again, something you've seen before. Here, we are looking at a slightly different situation where it's like an LED, but like I said before, then LED is a good solar cell, so they're equivalent situation, so don't have to get confused. Let's think about a case where light is emitted from that point here, okay? And you can see there are many rays here, so let's try to follow a few of them to see what's happening. The one easy one is going up. Of course, it is within its incident angle is less than the critical angle, so it will simply refract out. So the critical angle is marked here. Then you have another ray whose angle is greater than the critical angle. Of course, it's totally internally reflected, so it's trapped inside. And same thing happens to a symmetric ray over here, as long as of course, the critical angle here at the bottom is different than the critical angle on the top, because here the refractive index and this n prime could be different, right? So I'm assuming n is greater than n prime here. So and you can also have escape cone over here as well. And this is a situation for an LED, but a very similar situation happens for solar cells as well, because you can imagine the light coming in rather than being generated inside the material. Now, how do you compute what is the fraction of light that escapes? That comes from the critical angle, sin theta c is 1 over n, and it comes from the solid angle. So solid angle, as of course we know, is the three-dimensional representation of the two-dimensional angle. So this can be written as the solid angle of a sphere is 4 pi, and 4 pi over 2n squared is the fraction of the angle subtended by the escape cone. So if you think about a cone around the critical angle, if the light falls within that cone, it will escape. As if the light falls outside that cone, it will be trapped. Let's call the escape cone. So the probability that a light ray inside the medium will escape is small. Why? Because this number is big. Because the index is big. No, 4 pi is what? 12, roughly 12. 2n squared for silicon is already 18. So a relatively small number. I mean, not insignificant, but relatively small. Another way to say the same thing is basically a small amount of randomness can give rise to this ergodic behavior. Go ahead. Mm-hmm. That is correct. Yeah, if the n is larger, in the index of gallium arsenide, I don't remember, but it's about the same as silicon, right? Yeah. So, but in general, you're right. Higher the index, of course, the better. But keep in mind, if this index is very high, you're also going to lose a lot of light reflected off from the top. So coming in is more challenging as well. Yeah, in the case of an LED, that's the case. Yes, that is correct. So gallium arsenide is used for LEDs, for instance. Yeah, that is correct. Now let's try to quantify this analysis with an approach, and the actual algebra is not so important, but the physics of how do we do the analysis is important. So let's look at this interface. Okay, light's coming from the outside, sunlight, and then this is, I'm going to say that's air, and this is silicon. Light is coming in. I incident is incident intensity. It's coming in at some angle phi, shown there. And what's going to happen, of course, part of the light is refracted in. Part of the light is reflected here, which is not shown. And yeah, and the loss and the cone is shown as well, escape cone. The fraction of the light, T incident phi, will be transmitted. Now phi is simply the incident angle, so it's just saying that it depends on phi. As we know, the reflected light depends on the angle, right? Large angles will reflect more than small angles. So this is just a transmission efficiency. So I can write the internal intensity is simply T incident. I'm going to ignore the phi for now, multiplied by I incident. So it's just the transmission efficiency. Now, I have to make sure conservation of energy is satisfied. So the transmitted light must be balanced with the light that's escaped. So if I have so much power coming in, that must be equal to the power that is escaping because I'm in thermal equilibrium. Otherwise, the materials start heating up, right, or cooling down. And this principle is simply called detail balance. And this is, by the way, we didn't talk about it in the context of solar cells, but this is the way you actually compute the efficiency of solar cells. So something to keep in mind. We talked about it briefly, but not in detail. Now, the internal intensity is isotropic. That's the assumption because it's ergodic. We assume it's randomized, so it's homogeneous inside the solar cell. So we can compute something using this very simple expression. So this B internal is the intensity per solid angle. So essentially, it is the brightness, which is intensity per unit solid angle, inside the material. If we integrate it over all the solid angles, which is basically this integral here, this can be quite simply calculated as shown here. The full solid angles integral over a sphere simply becomes that from 0 to pi over 2. Okay. Now, and because there's a factor of 2 there, a 2 pi is taken out. That's how you get the solid angle integral over a sphere. That's just simple calculus. I'm not going to go over through it very carefully, but this is a very simple integral to do, right? This B, if we assume that this B internal is independent of angle, I can take it out of the integral, put it outside, and then the rest of these terms are a simple thing to do. Sine theta over 2 is just an integral of sine theta, just becomes cos theta, right? I think you all know how to do these things. So in other words, this integral sine theta cos theta d theta simply turns out to be half, because it's half sine 2 theta and 0 to pi, it just becomes 1. Anyway, this factor of 2 here comes from the extra pass due to the reflective back surface. I didn't talk about it, but remember in the previous example, we had a mirror at the bottom which reflects the light back into the material that gives it an extra pass. That's where the factor 2 comes from. So you end up with a very, very simple expression that internal intensity is 2 pi times B, which is the brightness or intensity per unit solid angle inside the material. Now, that is what is inside the material. Now, we can also compute the intensity of light that is escaping from this material. It's exactly the same integral, but now done over the escape cone instead of the entire sphere. So it's the exact same integral as shown here, except that now instead of 90 degrees, we're doing theta c. There's an extra term here, which we didn't see, but that's just the probability of escape. It's just meaning some of the light's actually reflected back because of Fresnel reflections. Not terribly important, because we're going to set that to be 1 later on. But just be aware that this factor exists. And then if we define an angle average escape probability, you can take that out of the integral. And then the integral simply becomes exactly the same as that. And you get a very, very simple expression here that escape intensity is equal to the intensity inside the material multiplied by this T bar escape divided by 2n squared. So what's outside is scaled down by 2n squared. So it's convenient because this is what we saw before. Okay. So with that, now we can try to apply detail balance, which is energy conservation. Light in must be equal to light out. So light coming in is the left-hand side. Okay, the transmission coming in, we saw incident intensity. Light going out is basically what we just computed here, right? This thing. And then if we put this term, put them equal, now we get a very simple expression for the internal intensity. Intensity is 2n squared times this term here. Now we're going to assume that this term here is approximately equal to 1, which is the probability that light transmits through an interface in one direction or the other direction are equal. That's not always true, but it's approximately true. For a black body radiation, you can show that it's actually true. So if you put that to 1, then you get a relatively simple expression that your intensity inside the material is 2n squared times intensity outside the material, which is nice because it's the exact same intuition we did think about in the beginning of this lecture. Now, we should be aware that in theory, you can actually exceed this limit. In some cases, there are some very interesting approaches where this has been exceeded. For instance, if you have a CPC with a very high concentration, this can be exceeded, but your acceptance angle is dramatically reduced. So there is a trade-off here, and that's where this brightness theorem comes into play. It's something we didn't talk about much, but the brightness theorem essentially is a formulation of the second law of thermodynamics, which we talked about when we talked about the concentration factors and how it affects its acceptance angle.